Today on AI Paper Podcasts, we are doing a deep dive into a really fascinating paper called ReMoRa, Multimodal Large Language Model based on refined motion representation for long video understanding.
Yeah, and this is a massive breakthrough for anyone dealing with a computational nightmare of video processing right now.
Absolutely. So let's jump right into the 1-minute summary so we have that locked in for the editors.
Go for it.
Okay, so the core problem here is that long-form video understanding is completely bottlenecked by the quadratic curse of standard transformers. Processing every single RGB frame of a long video is just way too expensive.
Right.
So the solution they propose is ReMoRa, and ReMoRa bypasses full-frame decoding entirely. It operates directly on the compressed HJ264 or HEVC video stream.
Which is such a smart pivot.
It really is. It uses sparse iframes for the appearance data and then compressed motion vectors for the temporal dynamics.
But, raw motion vectors are notoriously noisy. So the paper introduces a huge innovation called the ReMoRa module.
Refined motion representation.
Exactly. And that cleans up those blocky codec vectors into dense optical flow proxies using a teacher-student training setup.
Right. And then to actually handle that massive sequence length, they bring in the HMSS module.
The Hierarchical Motion State Space module.
Yes, which is based on Mamba.
Yeah.
So they use state space models to capture long-range dependencies in linear time. And the end result is that ReMoRa outperforms major baselines like LongVideoBench and Qwen2VL on benchmarks like LongVideoBench, NExT-QA, and MLLM.
All while slashing GPU memory usage by roughly 50%.
Yep. Efficient, accurate, scalable. So that's the headline.
Quite a headline.
It is. Okay, so that's the short version out of the way. Let's really get into the weeds here because, as someone who has tried to fine-tune video models in the past, reading the phrase outperforms with half the memory sounds almost like clickbait.
Oh, for sure. It sounds like magic. But when you break it down, it's really just incredibly elegant engineering. It all starts with the authors acknowledging that our current paradigm for video AI is fundamentally broken.
You're talking about the whole image-to-video approach we've been stuck on.
Right. For the last few years, the standard playbook for video understanding has been to basically treat a video like a flipbook.
Just a stack of photos.
Exactly. You take a powerful image encoder.
Like CLIP or SIGLIP or something.
Yeah, CLIP is the classic one. And you just run it on a stack of individual frames. So if you have a short 10-second clip, you extract maybe 8 frames total. Run them all through the image encoder, and then feed those resulting tokens straight to a large language model.
Which, that works totally fine for a short TikTok clip.
Sure, it's fine for that. But this paper is specifically targeting long video understanding. We are talking about minutes or even hours of footage.
Right.
And if you try to feed a 2-hour movie into a standard transformer architecture, you run squarely into a wall. The quadratic complexity of self-attention.
Let's actually unpack that for a second. For the junior engineers listening who might just use transformers out of the box, why exactly does it explode like that?
So, in a standard transformer, the self-attention mechanism works by calculating the relationship between every single token and every other token in the sequence.
Right, to build context.
Exactly.
Yeah.
But mathematically, that means if you double the sequence length, the computational cost doesn't just double.
It quadruples.
Yes. Big O of n squared. It scales quadratically.
So if a 1-minute video costs, let's say, X amount of compute to process, a 10-minute video doesn't cost 10x.
It costs 100x.
Which is just completely unsustainable.
It's impossible. So because of this math, researchers have been forced into this terrible trade-off when dealing with video. Sampling.
Right. You basically have 2 bad choices.
Exactly. You can try dense sampling, where you look at every single frame.
Which we just established is mathematically bankrupt for long videos.
Right. Or you do sparse sampling.
And sparse sampling is what practically all the big models are doing right now, right? They just grab one frame every 5 seconds or so.
Yeah, pretty much. But that introduces a massive flaw, which we call the blink and you'll miss it problem.
Oh, I love this example. So say I drop a set of keys on a table. The actual action of the keys falling takes, what, maybe half a second?
Barely half a second, yeah.
So if your model is only grabbing a frame every 5 seconds, it samples the frame right before I drop them.
You're holding the keys.
Right. And the next frame it sees, 5 seconds later, the keys are just sitting on the table.
And the model has absolutely no idea how they got there.
Exactly. Did I place them down gently? Did I throw them? Did they fall from the ceiling? It just doesn't know.
It's completely blind to the temporal dynamics between those snapshots. So what does the model do? It hallucinates. It guesses the action based on the static context.
Because it loses the video part of the video. It's essentially just analyzing a slideshow.
Precisely. And this is what leads us directly to ReMoRa's big aha moment. The authors stepped back and looked at the actual video file itself.
Like the actual MP4 or MKV sitting on your hard drive.
Yes. And they realized something profound. We are throwing away incredibly valuable information that is already baked into the file format.
Because the compression algorithm already did the math.
This is my absolute favorite part of the paper. Modern video compression algorithms, like H.264 or HEVC, they've already solved the exact problem of separating static content from moving content.
We're talking about the group of pictures structure here, the GOP.
Right. When a codec compresses a video, it doesn't store 30 completely separate full-resolution images every second.
That would make file sizes absolutely massive.
Unusable. So instead, the codec stores one full, high-quality image to anchor the scene. That's called the iframe.
The intra-coded frame.
Yep. And then for the next chunk of frames in that second, it doesn't store pixels at all. It only stores the changes from that initial anchor.
And those are the P frames and B frames, predictor and bidirectional frames.
Correct. And the crucial thing here is that those P and B frames achieve this using what are called motion vectors.
Okay, let's visualize this for everyone listening. What does a motion vector actually look like to the computer? Like, practically speaking.
Okay, imagine a grid overlaid on top of the image. A motion vector is basically just a really simple instruction for one specific little block of pixels on that grid.
Like a 16 by 16 square.
Exactly. It's a command that says, take the 16 by 16 block of pixels currently sitting at XY from the previous frame and just shift it 3 pixels to the right.
So it's not visual data at all. It's not RGB values. It's literally just a vector displacement field.
Exactly. Just a grid of arrows. It is incredibly lightweight data. It describes the dynamics, the movement, without constantly redefining what the object looks like.
So ReMoRa's whole core thesis is basically asking the AI community,
Why are we doing this the hard way?
right, why are we uncompressing these efficient vectors back into heavy RGB pixels, running them through a massive, expensive image encoder?
Just to try and force a neural network to relearn the exact same motion that was already explicitly written in the metadata of the file.
It's wildly inefficient when you frame it that way. We're basically reverse engineering the motion that the codec literally already calculated and handed to us.
Exactly. But, and this is a really important but, there's a very good reason why researchers haven't just easily plugged raw motion vectors into AI models before now.
Because they're incredibly ugly.
They are so ugly. We say they are noisy,
Yeah.
but honestly, they're just a mess for a neural net.
Why is that?
Because H.264 was designed to trick human eyes, not to provide clean data for computer vision. It uses block-based processing, so everything is chunky.
Oh, and it quantizes the data, right?
Heavily. It rounds off the vector values constantly just to save a few bits of storage.
So if you actually extracted and visualized the raw motion vectors from an MP4, it wouldn't look like smooth, fluid, natural motion.
Not at all. It looks like a jagged, blocky grid of arrows that occasionally just misaligns completely.
And if you just casually feed that dirty, jagged data straight into a large language model,
The network gets completely confused.
Yeah.
It tries to interpret the compression artifacts as actual physical features in the world.
so it might look at a weird, jagged, blocky edge caused by low bitrate compression and think, oh, that's a new object.
Exactly. It thinks the compression glitch is an entity. Which leads us to the very first major technical contribution of this paper, the RMR module.
Refined motion representation.
This is essentially the cleanup crew. The authors knew they couldn't just use the raw, dirty vectors, so they built a dedicated module to upsample and refine them.
But how do they actually train a module to turn bad data into good data? They need some sort of ground truth to aim for, right?
They do. So they used a teacher-student approach. They brought in a state-of-the-art dense optical flow model called CoTracker 3.
Oh, CoTracker 3 is fantastic.
It really is. It gives you pixel-perfect, beautiful motion tracking.
But it's way too heavy.
Way too heavy. You could never run CoTracker 3 in real time for a 2-hour-long video. It would take weeks.
So they use CoTracker 3 just to create the answer key during training?
Exactly. They feed a bunch of training video into CoTracker 3 to get these perfect, smooth flow maps. Then they take the cheap, ugly, blocky motion vectors straight from the codec of that same video.
And they train the RMR module to take the cheap, blocky input and predict what the expensive CoTracker 3 output would look like.
Precisely. It learns the mapping between the noise and the ideal signal.
That is incredibly smart. So then during inference, when a user is actually running ReMoRa in the real world, we don't need CoTracker 3 at all.
We throw it away. The RMR module has completely learned how to essentially hallucinate the high-quality optical flow just by looking at the low-quality vectors.
It turns the noise into signal on the fly.
Yes. So now ReMoRa suddenly has access to this stream of incredibly high-fidelity motion data, and it's getting it computationally almost for free.
Wow. Okay, so we've solved the input bottleneck. We have clean motion data from the vectors, and we have sparse visual data from the iframes.
Yep, the data is lean.
But we still have the sequence length problem. I mean, even if the token representations are highly efficient, a 2-hour movie still generates a massive sequence of tokens.
Hundreds of thousands of tokens.
And we still can't push that through a standard transformer because of that big O of n squared complexity we talked about earlier.
Right, which brings us to the second major innovation. Enter the HMSS module, and specifically, the star of the show right now, Mamba.
Oh, Mamba. Mamba is having such a huge moment in the research community.
It's everywhere. And for good reason. It's based on state space models, or SSMs.
Let's do a quick detour. For the engineers listening who maybe haven't had a chance to play with Mamba yet, what is the quick elevator pitch difference between Mamba and a traditional transformer?
So a transformer has a global receptive field. To understand a sequence, it literally looks at everything at once. Every token looks at every other token simultaneously.
Which is why the memory blows up.
Right. Mamba, on the other hand, is recurrent. It reads the sequence linearly, one step at a time, and it maintains a highly compressed, hidden state that evolves as it reads.
It updates its memory as it goes.
Exactly. And the massive game-changing advantage here is that Mamba scales linearly.
Big O of n.
Yes. Big O of n.
So suddenly, processing a 2-hour movie becomes feasible because the memory requirement just scales up flatly alongside the video length, rather than exploding exponentially.
You nailed it.
Yeah.
And ReMoRa implements this Mamba architecture in a really clever hierarchical way. That's what the H in HMSS stands for, Hierarchical Motion State Space.
They break it into 2 stages, right? Intra-GOP and inter-GOP.
Let's walk through those.
Okay, so intra-GOP, that's inside a single group of pictures.
Yes. Think of a GOP as a roughly 1-second chunk of video. Inside that specific 1-second chunk, you have one static iframe showing you the scene, and then a stream of those newly refined motion vectors showing you the movement.
Got it.
The intra-GOP Mamba block fuses those two things together. It essentially asks the system, okay, given this static picture of a kitchen and this vector motion of a hand moving downwards, what happened in this specific second?
It compresses that entire second of raw visual and motion data into a dense semantic summary token.
Exactly. It summarizes the local action. Then the second stage takes over, the inter-GOP stage.
The global stage.
Right. It takes all of those individual 1-second summary tokens and strings them all together using a bidirectional Mamba mixer. This is where the model actually comprehends the long-term storytelling.
So the mental model is, look at the local second, summarize what just happened, and then look at the whole movie globally to connect all those summaries together in time.
It's a beautifully elegant way to balance fine-grained local detail with massive global context. And because both of those stages are using Mamba, which has linear complexity, the whole pipeline stays incredibly fast.
Well, let's actually talk about the numbers, because the paper claims this architecture isn't just significantly faster and lighter, it claims it's actually more accurate.
And the benchmarks absolutely back that up. They tested it rigorously. On LongVideoBench, ReMoRa scored a 60.8. On NExT-QA, it hit an 84.2.
And what were the main comparison models they went up against?
The big ones. It beat both LongVideo and Qwen2VL.
Wow. What's crazy to me is that LongVideo is an absolute beast of a model.
It's massive.
It uses huge resources. And ReMoRa beat its accuracy while using significantly less memory.
Less than half, actually. During inference, ReMoRa uses about 10.59 gigabytes of VRAM.
Okay.
LongVideo uses 23.21 gigabytes.
That is such a critical hardware threshold.
It really is the dividing line.
Yeah, because 24 gigabytes basically means you have to use a data center A100 GPU or at least a really expensive RTX 3090 or 4090.
Which shuts a lot of researchers out.
But 10.5 gigabytes. That means you can run this model locally on a mid-range consumer graphics card. You could legitimately run this video analysis on a decent gaming laptop.
It completely democratizes long video understanding. You don't need a massive AWS budget to analyze a movie anymore.
I really want to look at the qualitative examples they provided because benchmark numbers can feel a bit abstract sometimes. The dog with the ball example in the paper really perfectly highlighted why this whole motion vector approach is vastly superior to just sampling still frames.
I love that example. It was a classic computer vision failure case for the baseline model.
Set the scene for us.
Okay, so the prompt video shows a person and a dog hanging out in a grassy backyard. And there's a blurry object moving around in the air above them. The baseline model, a LongVideoBench, looked at the footage and very confidently stated that the person was throwing a frisbee.
Which is totally wrong. But why did it guess frisbee?
Because it was only looking at a few sparsely sampled static frames. In a still photo, a fast-moving ball is just a blurry streak.
Right.
So the model sees the semantic tags park plus dog plus flying object in air, and its training priors immediately yell, frisbee.
It just hallucinated the object based entirely on the background context.
Exactly. It guessed, but ReMoRa didn't guess. ReMoRa correctly answered that the person was bouncing a ball.
And it knew that purely from reading the motion vectors.
Yes. Think about the physics. A frisbee has a very smooth, horizontal, gliding trajectory.
Right.
But a bouncing ball has a very distinct, vertical, rhythmic, up and down trajectory that is subject to gravity. ReMoRa's RMR module literally saw that vertical oscillation pattern in the vector field.
It didn't even need to see the high-resolution pixels of the ball itself. The pure physics of the motion mathematically revealed what the object had to be.
That is the magic of this approach. The motion itself is the semantic signal.
That is such a profound insight. There was another qualitative example, too, about a guy on a spiral staircase.
Yeah, the railing slide.
Yeah.
So the video shows a man sliding rapidly down a staircase railing. And the baseline model confidently said he fell down the stairs.
I mean, if you're a dumb model looking at sparse frames of rapid downward motion on a staircase, falling is a pretty reasonable statistical guess.
It is a logical guess if you're blind between frames. But ReMoRa didn't say he fell. It said he slid down, landed, and then checked his pants.
Which is such a massive difference in interpreting the actual narrative of the video.
Huge difference. And it all comes down to continuous tracking. The baseline model probably completely missed the landing because the landing happened between its sampled frames.
Oh, the blink and you miss it problem again.
Exactly. ReMoRa, however, tracked the entire continuous slide.
Yeah.
But crucially, it tracked the stabilization at the bottom.
It saw the motion vector field suddenly drop to 0 when he hit the floor.
Yes, a sudden halt. And then immediately after that halt, it detected very small, subtle motion vectors localized specifically around the man's hands and pockets.
So it caught the nuanced action of checking his pockets because it literally never stopped watching the vector stream. It's experiencing the flow of time, not just looking at a photo album.
Exactly. It's true video understanding.
Let's pivot and dig into the ablation studies for a minute, because this is where we actually see if all these fancy components matter. What happens if you take ReMoRa and just turn off that RMR refinement module?
They tested exactly that. If you bypass the RMR and just feed the raw, blocky H.264 vectors directly into the Mamba backbone, performance takes a massive hit. It drops by about 2 full points on the NExT-QA benchmark.
Which conclusively proves that the whole teacher-student training setup with CodeTracker 3 isn't just some academic gimmick. It is strictly necessary to bridge the gap between noisy compression artifacts and actual semantic understanding.
Absolutely. Garbage in, garbage out. You have to clean the signal first. But, there's another ablation study in the paper that I actually found even more interesting. It was regarding their sampling strategies.
Oh, right. The scene adaptive sampling versus uniform sampling.
Yeah. So traditionally, when researchers process video, they just use a uniform rule. They tell the system, give me one frame exactly every 4 seconds, no matter what. That's uniform sampling.
But ReMoRa does something much smarter. It listens to the codec.
Exactly. It lets the file dictate the pacing.
Because H.264 naturally puts iframes at scene cuts, doesn't it?
Yes, exactly. Think about how a codec works. If the camera angle suddenly cuts to a completely different room, the compression algorithm is forced to create a brand new iframe.
Because all the pixels just changed, so the motion vectors from the last frame are useless.
Exactly. The old anchors are gone. So ReMoRa uses these natural algorithmically generated breakpoints as its sampling moments.
And when they forced the model in the ablation study to ignore those natural scene cuts and just use a dumb uniform sampling rate,
performance got noticeably worse.
It makes perfect sense. The structure of the video file is essentially a pre-computed table of contents. The codec has already done the heavy lifting of segmenting the video into logical scenes for us.
We've been fighting the file format for years. We've been treating video like a raw, dumb stream of pixels, when in reality, a compressed video is a highly structured, semantically rich document. ReMoRa finally works with the grain of the data instead of against it.
It's brilliant. However, we do have to be objective here. No single paper is perfect, and this one is no exception. Where does ReMoRa actually struggle in practice?
The authors included a very honest error analysis section. The biggest lingering issue for ReMoRa is spatial precision.
Like identifying exactly where is the cat in this room?
Kind of. It's more about granular spatial relationships. Like, is the coffee cup a few inches to the left or the right of the laptop?
Ah, I see.
Because ReMoRa relies so heavily on the motion vectors for its continuous understanding and only uses very sparse iframes for the actual appearance data, it can sometimes lose that pixel-perfect spatial grounding.
Right. If a question relies entirely on analyzing static spatial relationships in a very complex, cluttered scene, a model that densely samples high-res RGB frames might still edge it out.
That's the core trade-off. You gain incredible temporal resolution, but you sacrifice a tiny bit of absolute spatial resolution.
Fair enough. Were there any other limitations?
The other main issue is temporal confusion in extremely high chaos scenes.
Even with the Mamba architecture.
Yeah, even with Mamba. If you feed it a scene where 10 different rapid-fire events happen simultaneously, like a chaotic action movie sequence, ReMoRa sometimes swaps the exact order of the micro-events. It absolutely knows what happened, but it might get the specific chronological sequence slightly jumbled.
So it's not a flawless historian, but it's still a highly efficient observer.
Exactly. It gets the gist of the chaos, even if it mixes up a detail.
I want to zoom out a bit as we wrap up. We're clearly seeing a major trend in the research here. Over the last year or so, we had Videollama, we had Alava, and now we have ReMoRa. But this specific shift toward Mamba and compressed domain processing feels fundamentally different. Do you think this is going to be the standard future architecture for video AI?
I really do. I think the combination of compressed input data plus a linear complexity backbone is just inevitable.
We have to go that route.
We have no choice. We are moving toward a world where AI needs to analyze day-long surveillance footage or entire seasons of TV shows at once or continuous always-on wearable camera streams.
Right.
We simply cannot afford to use quadratic transformers for that.
The math just literally doesn't work at that scale. You'd need infinite compute.
It doesn't work. And conceptually, what I love most is that ReMoRa fundamentally challenges the old, lazy idea that video is just a tall stack of images.
You know, it really reminds me of biology.
How so?
Well, think about how the human eye works. Our retinas don't capture 30 full 4K resolution frames every single second and send all that raw pixel data to the visual cortex.
No, the optic nerve would completely melt trying to carry that bandwidth.
Exactly. Our peripheral vision is basically just a highly tuned motion detector. We are wired to see change.
Right.
If something in our field of view isn't moving, our brain essentially compresses it. We stop actively updating that specific part of our mental model just to save metabolic energy.
That is a fantastic analogy. In a very real way, H.264 compression is biomimetic. It intrinsically prioritizes tracking change over redundancy. ReMoRa is just finally aligning our AI architecture with that exact same biological principle.
So by stopping this brute force decoding of every single pixel, we might actually be building computer vision systems that fundamentally see the world a lot more like we do.
It's a really compelling thought to leave on. Maybe the secret to achieving true human-level video understanding isn't just throwing more raw compute at the problem.
But just building better filters.
Exactly. Working smarter, not harder.
Well, for all the researchers listening, the code and the models for ReMoRa are open source. If you want to check out the specific architecture diagrams, and I highly recommend looking at that teacher-student loss function setup for the RMR module, the paper is ReMoRa, Multimodal Large Language Model based on refined motion representation for long video understanding.
It is a dense read, but it is absolutely worth it for the Mamba implementation alone.
Thanks for tuning into this deep dive. Keep experimenting, and we'll catch you on the next one.
See you then.